So hopefully you've been studying and preparing for that. It's in the testing center in PSA in the basement. So you need to take your student ID card with you and a pencil, and that's really it. You can bring a graphing calculator as long as it's not a TI-89. It's not really going to help you, but you can bring one if you want. And if you don't own one, you can check one out in the testing center. It's going to be 18 multiple choice questions and then 10 points worth of free response. So that's the format. Don't be fooled. Multiple choice can be hard when well written, and I think it's pretty well written. So don't let that influence your studying, okay? Study just as we've been doing work in class, right? You want to focus on the concepts and the process and the big ideas. I'm not going to suddenly give you a test where all of a sudden I'm asking you to do a bunch of computations, right? That would be weird because we haven't been doing that all semester so far, right? So yes, so that's what you need to know. I have office hours today after class, and you can go into that testing center anytime between 10:30 and 6:30 tomorrow. You can take as long as you want. Now, if you go in right at 6:30, you will get kicked out by 8 p.m. So if you want more than an hour and a half, then you better get there sooner. So you can, if you want though, you can wait until you can go to Mark's office hours tomorrow from 11:30 to 1, and then go take the test after that if you have some last minute questions. Okay, there was a question? I already answered it? I think it's just 8. 8 p.m. Is when they want to go home. Okay, question. 10:30. Okay? And you have to have your student ID. They won't let you in without it, okay? All right. So I think that's what you need to know about the test. It will cover everything up to constant rate of change, including some of the stuff that I'm talking about today, okay? So let's get to it. So we started talking about constant rate of change on Monday. So let's sort of revisit the key ideas. So the meaning for constant rate of change consists of 2 pieces. We've got 2 quantities that are changing simultaneously, and changes in one quantity are proportional to changes in the other. That's the scenario in which we can talk about constant rate of change, okay? And so we have a multiplicative representation of this. This is the changes in y are multiples of changes in x. That's what this sentence says. And then we can also represent that as a quotient, right? And so when we represent this as a quotient, this delta y over delta x equals k. This k value is the constant rate of change. Okay, that's what k represents. Okay? So far, so good? Hope so. So we talked about this kind of example last time, where when we looked at these bars, we said the changes in y relative to the changes in x are 2.1, right? So delta y is a multiple of delta x, and that multiple is about 2.1. Okay. Now, something that I didn't put in this picture was what happens if we aren't just talking about the changes, right? Because when I have this bar diagram, delta y and delta x, changes in y and changes in x, right? I'm talking about 2 quantities. I'm talking about x and y inherently, right? I can't be talking about the changes in x and y unless x and y are actually present. So something that I want to draw your attention to is that I could have had some amount of just y over here, right? And some amount of x over here. And those 2 quantities don't have to be in some proportional relationship, right? Well, I mean, inherently they are. You could always describe that. But when I change delta, when I change y and I change x, it's the changes that I want to focus on as being in a proportional relationship. Okay. So, you know, the y that I have up here would be the same y here, you know, that fixed amount, and this would be the same x there, right? And again, down here. So, right, okay. So what I want to do now is actually look at a concrete example. So we've got this. After a car goes under a bridge, it travels at a constant speed of 72 miles per hour, meaning that the number of miles it travels for some period of time is always 72 times the number of hours in that period of time. Okay, so what I want you to do right now is identify x, y, delta y, and k in this scenario. You can talk to a neighbor if you want. All right, let's bring it together. Is Scott Moore here? So can you tell me what you said x was?
X be the change in time.
Is x the change in time? Well, so delta x, I agree, would be the change in time. So this is amount of time during some period, right? So change in time. Right, because they said in some period of time, okay? All right, so if delta x is an amount of time during some time period, then x itself must be what? So time elapsed since what happened? So this is time in hours, hopefully, since car passed under bridge. How come this is so much more specific sounding than the delta x? Yes?
Because while delta x is just looking at the overall time, x looks at, in this case, looks at just a specific time, so it has to be more specific. Because, well, you could say, well, x can equal time. What time? Time after? Time since went under the bridge? Time after went under the bridge?
Yeah, exactly. So whenever we talk about a specific x value, we need some frame of reference. There's some specific referent to which we are referring time since what. Whereas the delta x is giving us a change in time. So, you know, from 10 seconds after the car passed under the bridge to 15 seconds, or I guess hours, after the car passed under the bridge, we could evaluate the change in time as being, you know, 5 hours. Did you comment?
I'm just confused by the concept. So, so if time since the car went under the bridge was an hour, 2 hours.
Yep.
The change in time, the amount of time during a period, it doesn't necessarily, the change in x doesn't necessarily have to be from when the bridge So,
Right.
because I thought that it was like the bridge for delta x and then like total time travel, including before the bridge, like that little thing
Okay.
that you drew before the
Mm-hmm.
flag.
So I see what you're saying. So in this scenario, I would say that it makes the most sense to say x is the time since the car went under the bridge. And delta x could be any time period. It could start when the car passed under the bridge, or it could start an hour after the car went under the bridge. Okay? That's a good question for clarification. Okay, so what about y? What is y going to represent? Number of miles traveled after going under the bridge. Great. Okay, what about delta y? So this is the number of miles traveled in the given period of time, right? Okay, what is K? 72. Where does that come from? So the car travels at a constant speed of 72 miles per hour, right? And so if we were to think about like what this whole sentence says, it's really saying that the number of miles traveled in some period of time is 72 times the amount of hours you travel, right? In that period of time. So this is our handy dandy go-to formula for constant rate of change. Another way that we could have written that directly coming from the speed, right? So when we saw speed up here, what's our other way of representing, or what is our way of representing speed? Speed is a quotient, right? It's distance over time. So we also could have said, oh, okay, well, so using the speed, change in distance over change in time is 72, right? But again, this version of the statement is equivalent to that one, okay? They're equivalent statements, just different perspectives on the same coin, okay? Are there any questions so far? Not too bad? Okay. Oh, I was kidding. So then, if we mix it up a little bit, so if after driving for a while, the car travels another 1.6 hours at a constant speed of 72 miles per hour, during that time period, the number of miles the car has traveled that day increases by 72 times 1.6 miles. So I want you to take a minute to do the same thing we just did, but while you're doing it, be very conscientious of answering the following question. How is this different than the first scenario? Okay. All right. So let's, good conversation. Sweet. So let's do it, right? So let's see, Madeline, help me out. What's X?
X is the 1.6 hours that you have been
Okay, so what you're describing is possibly changing the setup a little bit so we don't start our clock until the beginning of this 1.6 hour period. Right, so the point is here, because it says after driving for a while, we don't actually know like what the X value is, right? At the end of this time period or at the beginning of the time period. We have no idea what that X value is. So this is a known time value, right? We don't know. What's Y? Some unknown distance value, right? We have no idea how far you've driven because we don't even know, right? Well, I don't know if I was driving 72 miles per hour for the entire time, right? Like, all right, so I was driving for a while after I went under the bridge. So maybe this original scenario lasted for, I don't know, an hour and a half, but then maybe I slowed down. Then maybe I sped up. And then we resumed this scenario. And, you know, so like crazy stuff could have happened. I don't know where I am, okay, after I've been driving for a while. But I do know in this scenario, what is delta X? 1.6. That's the amount of time that I'm focusing on for driving for 1.6 hour time period, okay? What's delta Y? So this is the distance traveled during that time period, which is 72 times 1.6. Where does that come from? So delta Y is K, which from above, right, we still know that we're traveling at a constant speed, so K is 72 times delta X. Okay, so we can get delta Y from that. Okay? Alrighty. Hopefully that's not too stressful. Is that okay for people? I mean, you could, but if you leave it this way, then I can see your process, which is nice. Mm-hmm.
When we're asked why, does it like y equals x times k, the same thing as like what you just said? Is it?
Yeah. So, is there a difference between stating that y equals kx and that delta y equals k delta x? Yes.
Yes, because y equals kx is like what you said is when we explain what y and x are, it has to be specific.
Okay.
So y equals kx is like a cardinal motion at a certain period in time, while delta y equals k times delta x is the cardinal motion over the period of time.
Okay, so I think there's good stuff there. So let's get super specific, right? Let's go back to that second example. So let's say that before I started that 1.6 hour time period, I had already covered a distance of, I don't know, 15 miles, right? So in that second scenario, where'd my guy go? So let's say that I cover 10 miles before I start measuring, you know, my 1.6 hour adventure, right? I'm going to call it that. Maybe it was an adventure. Maybe I had some really good music on. Okay, so then what happens? If I were to compare at the very beginning of that scenario, what's going on? Well, y, which represents the distance traveled at, you know, the start of this scenario, is 10. If that satisfies a y equals kx relationship, then I should have this, right? Because at the beginning of that time period, that's the beginning of the time period, time is 0. Is that okay? That forces, oh, I got a no. A no shake?
I was gonna say you can't pick something multiplied by 0 and get
Yeah, that's a problem, right? So, and then, so, but so let's ignore that fact for a second. I don't know how, but let's pretend that we could ignore that fact for a second. Then in another hour, right? I've been traveling, so during this time period, I'm traveling at 72 miles per hour. If I travel an hour, what's the total distance I've covered? So I cover 72 miles in that hour, but remember, I had already covered a distance of 10 miles. So my total distance, i.e. my y value, is going to be 82. And if this is maintaining a proportional relationship, then that should equal this same k times 1. This is an impossible situation, right? You can't have the same k work in both of these equations. Okay, but if we were to talk about the changes, right? So delta y at the very beginning, we're claiming this relationship, right? Well, at the very beginning of the time period, what is the change in distance? At the very beginning, when you start your clock, the change in distance is 0, right? So here we actually get 0 equals 72 times 0, right? And then an hour into it, what is the change in distance? 72 miles, right? And that was 1 hour into it. And we could do that again for a different amount of time in the first 1.6 hours. And no matter what time we choose, the distance covered will be 72 times that amount during that period of time, okay? So this relationship is maintained with the changes, and it's not maintained with the actual values, okay? Bless you. Question?
I had, like, for the one we're talking about when y is your distance from LA, then your distance from LA is decreasing.
Yeah.
So your speed is like going to be negative 52 miles an hour, negative 7, whatever it was.
Okay.
But your constant is supposed to be 57. So I was like, well, the constants are like inverse of each other. So like, I didn't know how to answer that question.
I'd have to look at it again. Can we talk about it after class?
Yeah.
Okay. All right. Super cool. So before I do no, let's do this now. Okay. So so what we've talked about so far is constant rate of change, right? And we started out with a representation of what that might look like by using our bars, right? I gave you a delta y bar and a delta x bar. And we talked about the relative size and how the relative size is the value of the constant rate of change. Okay, but as we talked about with other quantities, bars aren't the only way to represent that, right? We talked about how you could graph the relationship between two quantities. And so I'd like to talk about now how we can represent constant rate of change in a graphical setting, okay? So when we have two quantities, x and y, that are in a relationship with a constant rate of change, the set of all points satisfying that relationship form a line, okay? Why is this so verbose? Well, that goes back to our conversation about how you represent two quantities relationship, right, as being a graph. And what is a graph? It is the collection of points satisfying that relationship. So that's why this second part, well, I did it again. The second part of that is such a long statement, okay? So let's take a look at it. So this might look familiar if you've been reading ahead. I think this is for Friday. But I wanted to talk about it in class. So the following graph shows the relationship of water pressure and height above the seafloor at a location where the ocean floor is 52 feet below the surface. Water pressure decreases at a constant rate with respect to the height. The constant rate of change is negative 0.44 psi per feet. Okay? And so we have a graph, of what that looks like. Now, I've already stuck it up here for you. So what I want to do is actually analyze what we're looking at. Okay? So when I talk about visual representations, what I am focusing on is these red triangular type things, right, along the graph. So if I wanted to see that there is a constant rate of change relationship, then what I am looking for is that delta y equals k delta x for some k and for any delta x and the corresponding delta y. Okay? So what I can do is I can take these three sets of information, if you will, and actually see if they produce a constant k, right? So let's see. So if I were to look at the change in y in the first part, so right here, okay? So the change in y was negative 4.4, and so we're hoping it equals k times delta x, right? So then if I were to solve for k, I get this. Oh, where'd you go? Okay, I can do it again, right? I can take the middle set and do the same thing. So hopefully when I do change in y over change in x, does that actually give me the same thing? If you type it into a calculator, it will. That's not a very convincing argument, is it? Are you convinced? Shoot. I didn't think about this. The numbers are not that simple. If you divide top and bottom by 3, what happens? You get negative 2.2 over 5. And notice if you divide this by 2, you get negative 2.2 over 5. Okay, cool. So that is the same k value that I got up there. And then if I do it again with the third set, it'll happen again. It's a beautiful thing, okay? So now, all right, now I feel like pretty confident in saying, okay, because any change in x that I looked at had a relative size to the corresponding change in y of negative 0.44, right? Then I can confirm that this, in fact, is representing a constant rate of change relationship. Okay, and then where have you seen this before? Well, this is what we call the slope of the line. So the slope of a line, right, is the value of the constant rate of change. Okay. So when you look at this, I want you to be very weary of just automatically going back to your old meanings of slope of like rise over run. If that's what comes to your brain when you think of slope, you want to try your darndest to erase that and try to think about relative size of changes in y and changes in x. That's what we're going for here, okay? How are we doing? So far, so good? Question? No? Okay. Let me know if you change your mind. So, what I want to look at now is another example in graphing calculator. And I'm going to be posting another assignment that's going to help you keep getting practice with all of this stuff, okay, with the graphing calculator program. I noticed in a lot of the emails I was getting about today's assignment that there were still some issues. And again, the reason why I'm promoting graphing calculator is because it literally won't work unless the mathematics you're doing is correct, right? So this is like your way of getting instantaneous feedback. If the program doesn't do what you ask it to do, it's because you asked it to do the wrong thing, okay? That means there's something awry in your mathematical notation or whatever it is, okay? Because the program knows math, and it will do the math that you tell it to do, okay? So, anywho, here's our scenario. You're going to hop into a taxi cab in Vegas, and the meter will immediately read $3.30. This is the drop charge made when the taxi meter is activated. After the initial fee, the taximeter will add $2.40 for each mile the taxi drives. In this scenario, the total taxi fare depends upon the number of miles ridden in the taxi, and we can ask whether it is possible to model this type of scenario with a function. Can we model this scenario with a function? Why? So what is the requirement to be able to model something in a functional relationship? Yes, sir.
Two quantities that covary directly.
Two quantities that covary directly. I think there's something to that. But technically, you can have a function where one quantity remains constant.
So,
Yeah?
we've been given a scenario where equal change in one and equal change in the other.
So, okay, so what I heard was we were given a scenario where for equal changes in one quantity, there are equal changes in another. Is that answering the question of whether or not this is a functional relationship? Yes.
I think you can use a function because it only asks you to put miles into the function and spits out the rate of the
Okay, so if I travel 2 miles in my taxi, is there a guess as to how much I'm going to pay? Or is there flexibility there? No, right? There is a unique value that the fare is going to cost me if I travel 2 miles. Okay, so I input number of miles, I output one unique value of the taxi fare. That's what makes this a functional relationship. Okay. Now, oh, question?
So, what if you went 1.5 miles?
Okay. This is, yeah. So how much are you going to get charged?
Would you just be, is there like a break in the function? Or?
Okay. So I mean, I don't know if everybody in here has ridden in a taxi before, but the meter runs as you drive, right? So it's not like you're going to only travel in integer values of miles, right? The taxi's not going to drive 3 miles if your hotel was only 2.5 miles away. So the meter will continue adding money as you're driving. So we're going to view this a little idealistically as a continuous situation. Okay. Now technically it can't be. You're very right in having this question because money is not continuous, right? It goes cent by cent. But we're going to pretend for a second that we could talk about money in a continuous fashion. Okay, so what did I want to do? I wanted to try to model this scenario with a function. Okay, so how do I do that? So we said that, what did we say? That this is a function. What is the input and what is the output? So you input miles driven, you output cost, right? The taxi fare. So, whoops, I don't want you. I want you. Oh, shoot. Too far. Don't listen. No. Turn. Ignore what you see. Okay, so let's say the cost, right? Now, if I just type C, Graph and Calculator reads this as a parameter. It assigns it a value of 1. So I want to turn C, big C, into a function. So I need to press Control parentheses to tell it that I'm working with a function. I could use, what do you want to call money? Or miles? M? Okay. So the cost in terms of number of miles traveled is going to be what? So you pay $3.30 no matter what. You step in that taxi cab, you are paying, okay? And then it was $2.40 M. Okay, so now let's think about why I was able to just write this relationship, okay? So if I were to imagine going back to my bars, right, then no matter what, I pay a cost of $3.30, right? but then the change in the cost relative to the change in number of miles driven is always 2.4, right? So if I've driven 0 miles, so this is M, then that's how much I pay, right? But then let's say I drive 1 mile, then that's going to go up $2.4 right there, right? What if I only drive another half of a mile? So now we're at 1.5 miles. Then this will lead to 2.4 times half, right, as this change, this additional little bit. So when I'm writing these numbers up here, I'm not writing the total amounts, right? I'm writing the changes, okay? So we can visualize this using bars, but we can also visualize this using a graph. And so now that I've actually typed in a function, am I ready to graph? If I press graph, is it going to graph? No. And this is where a lot of people emailed me. I don't understand, it's not graphing. Okay, it's not graphing because you haven't told it to graph yet. What you've done at this point is defined a function. That does not instantiate a graph. So let's instantiate a graph. So I need a new control or a new command line, and I want to say that on the vertical axis, so on the y-axis, y should equal big C control 9 of x. Okay? Because y and x are what graphing calculator knows for the vertical and the horizontal axes. So I'm not going to type y equals c of m, because if I do, what will happen if I type c of m? What's the value of m? So to us, m is the number of miles. To graphing calculator, m is 1. It's a parameter, okay? So it automatically assigns it a value of 1, okay? So I don't want to use m, I want to use x. Now if I press graph, will I get a graph? I will, right? Bam, there's my graph. Okay, does it make sense for this graph to continue forever to the left? No. So how can I modify that so that it accurately depicts the scenario? We need x to be greater than or equal to 0. So now when I graph it, I get a more accurate representation of the scenario. Question? In my computer, it's option and then the greater than. Control Shift if you're on a PC. Okay? And again, that's on the graphing calculator shortcut list. Okay? That's on Blackboard. Okay, so great. So we have our function. Now I want to identify a point. Okay? Yep.
Can you change those colors from green and blue to like dark green? Yeah.
Thank you. Okay, so you just click on the box and you get choices for colors. Okay? So now I want to identify a point. So the way you identify a point is you create a 2 vector, okay? And you see it, so instead of writing parentheses, x value, comma, y value, graphing calculator reads vectors. It's the same idea, just different formatting. So let's say I want to know, let's see, so we'll go with our bar graph, right? So we traveled 2.5 miles in our bar graph, so I want 2.5 miles. Should I sit here and add up all of those values on the top line? Yeah. I went to math and 2 vector. Okay? And this will be in a document that I'm going to be putting on Blackboard. Okay? So, but do I need to add up all of these numbers up here? That sounds annoying. What could I do? So the y value should be C of what? 2.5. No need to do those computations because we've already defined a function that will spit out the cost of the taxi fare after traveling X number of miles. Okay, so let's make that red, and we'll graph it. So now you see that point is right there. Okay? So once again, so let's actually, not once again, let's actually interpret this point. What does this point tell me? Miles. Okay, so this point tells me that if I ride my taxi for 2.5 miles, the cost of the taxi ride will be about $10. Okay? Super cool. So that does nothing as far as describing to me constant rate of change, right? So how am I going to now visualize what I have up here in the bars on my graph in terms of constant rate of change? Yes?
Could you do the little triangle?
Yes. So let's talk about how we make those little triangles, okay? Because once again, graphing calculator speaks the language of mathematics. So I can't stand here and say, I want triangles, right? I have to actually construct said triangles, okay? So how do we do that? Let's say I want to suppose that my hotel is 2 miles from where the taxi picks me up. And I have a great idea to stop for food before going back to the hotel. But my favorite restaurant is going to add 1.7 miles to the trip. How much extra will this cost in cab fare? Okay. So notice I'm talking about changing the amount of distance that I'm going to cover, right, by 1.7 miles. And I want to specifically identify the corresponding change in cab fare. How much more is it going to cost me than if I had just traveled 2 miles in the first place? Okay, so ideas? Before I type any math, where on this picture am I going to end up drawing? Let me, whoops, this way. So where, oh, we've got hands. Cool, yes.
So you plot the value at x equals 2 and x equals 3.7.
Okay, so at x equals 2, that's how much it would have cost if I went straight back to the hotel, right? But I decide to detour and go get food. That's over here, right? So if I want to keep track of all of the quantities involved, then I would need a horizontal line going this way. What does that represent? Change in distance, right? The increased number of miles to go get my food, okay? And then I would need a vertical, close to vertical line. And that's going to represent what? This is change in y, which in context represents the increased cost of going to get my food, okay? Not counting the price of the food. Okay, so how do I make those things appear mathematically, okay? Well, what are those things? So this horizontal line, right? That's a line. How do you represent a horizontal line mathematically? Y equals something, right? What is the something that this equals? Y equals 2? Yeah, so this value, this y value here, is c of 2, right? And then the y value up here is c of 3.7, right? And then this was 2, and this was 3.7. Okay. So, all right, so let's go ahead and make the magic happen. So, ooh, okay. So, if I want to create a horizontal line that only goes the length of delta x, I'll get it started. What is that going to produce?
A line that goes
An infinitely long horizontal line. How do I restrict it? So I need x between okay. All right, I'll make it red. Okay. What about the vertical line? So to get a vertical line, right, so this line is characterized by the fact that every x-coordinate on it has the same value, and that coordinate is 3.7. So x equals 3.7. But I don't want the entire vertical line. How do I restrict it?
less than C of 3.7 greater than C.
Okay, so remember, this vertical line segment is restricted by these y values. So I need for C of 2 to be less than or equal to y to be less than or equal to C of 3.7. Do we think it's going to work? Are we ready? Ready, set, go. Okay. So again, the point of this was to get you thinking truly mathematically, right? So I want to be thinking about this vertical chunk as the change in y. How do I get those values? I look at the value of the function in one place, and I take the difference, right, to get to the value of the function in another place. So that's our change. And likewise on the horizontal. Okay? Yes?
Why is it necessary to I know it's necessary.
So C of 2 comes from wanting it to be bounded below, right? So I want only to go down to there. And this value comes from this point. Well, because the value isn't 2, right? This is the ordered pair 2 comma C of 2. So the y value is C of 2, right? Okay. All right, guys. I have office hours now. If you missed attendance, you should come talk to me. And Mark has office hours tomorrow. Good luck with the test.
This is some.
Sorry, I just need to pause the recording.